There you go.
Welcome to the Saturday night presentation from United Astronomy Clubs in New Jersey. Tonight we'll be talking a little bit about the South Pole Telescope, the Ice Cube Observatory, and space weather research in Antarctica. Excuse me. You saw the setup I have here, you'd kind of laugh. There's a cell phone taped to books, and we hope the whole thing doesn't fall down. But anyhow, here goes. I'm Gil Jeffer. I work for NJIT, New Jersey Institute of Technology, Center for Solar Terrestrial Research. I'm a research engineer there. I'd never had the privilege of going to NJIT, but I got to tell you, if you have any interest in physics or know anybody else that does, it's a fantastic place to go to school. Really interesting with good instructors. This is a picture from, I think, 3 years ago down in Antarctica after digging out some snow. You can tell it gets a little bit cold down there. So the first thing I'll talk about is the South Pole Telescope. It's one of the major projects down there, which we had nothing to do with at NJIT, but it's kind of interesting. This picture is taken in the winter. You can tell because it's dark. Once you're in Antarctica, you have basically 6 months of light and 6 months of dark. The South Pole Telescope is 10 meters in diameter. Very big scope, and it works in radio frequencies. It's basically to study cosmic microwave background, and it had two main purposes. The first is to find distant massive clusters of galaxy through the interaction with the CMB, the cosmic microwave background. And the second survey is to measure the B mode or the curl component of the polarized CMB, and to do that to determine the constraints on the mass of the neutrino and the energy scale of inflation. So I'm going to go way back to the beginning here and talk a little bit about the Big Bang. Big Bang was actually came about, I think the first time it was thought of was in the 30s or 40s, I can't remember the year. But then they started trying to figure out, well, how come the universe is so uniform, but not quite? And they came up with a theory of inflation. And this graph here basically shows the age of the universe and how things progressed up to the current date. Up on the top, you'll see gravitational waves. So those are actually, oops, what's going on with the camera? Don't do that.
It's not right.
No, it's not.
Locate your device. Well, we don't know how to fix it, guys. I don't know what to tell you. It's showing on the screen sideways.
Well, turn your head sideways. I don't know what to do.
Yeah, y'all just need to turn your screen.
Well, now you turn on the light, because now turn on the light. Okay, turn it off again.
You got it.
Anyhow, I don't know what's going on here. What?
Well, first of all, that was the wrong way, so keep going.
Okay. Well, sorry about that. It's probably going to continue going like this, I guess. I don't know why it's turned. But basically, this shows the age of the universe as from the Big Bang till now. Inflation occurred very early in the universe, 10 to the minus 30 seconds. It was seconds. It was all over with and done with. And now we're at 13.8 billion years. But those gravitational waves, which were formed, in theory says were formed during inflation, should still be propagating through the universe now. And part of the reason that they're using the South Pole Telescope is to detect those gravitational waves by the imprint of the polarization signals that would be on them, the B mode polarization. I'm sorry this is turned. I have no idea how. But you've probably seen the pictures. Oh man, this is terrible. You've probably seen a picture of the CMB before, and it looks, well, let's go back, God's sake. Inflation happened very early in the universe. The CMB basically is what the signal is traveling to us right now, to the present day. Why do you see it in a microwave? When the universe was first born, visible light, when it first escaped, basically, was in the near infrared and the red end of the spectrum. But if you look at sound, you basically, when you have an ambulance coming away toward you and going away from you, you have a different sound. You have basically the Doppler effect, which you can hear with this. maybe. Nothing's working today. Well, maybe you can't. Anyhow, good grief. The electromagnetic spectrum is the same thing. The universe is expanding, and as a result, the wavelengths are getting stretched out as the things move faster and faster and further away from us. So the light that started out at the red end of the spectrum is now pushed down into the microwave end of the spectrum, way down here. And that's why they look at the cosmic microwave background. Penzias and Wilson basically discovered CMB on May 20th in 1964, which was about 54 years ago almost exactly. They didn't know what they found. They built this big horn antenna to listen to the Echo satellite, and they kept getting interference on it. Couldn't figure out what the interference was from, so they tried all sorts of things, including taping over all the welds, cleaning out pigeon droppings and everything else, but they still got, no matter where they pointed it, they'd get in for interference. In the meantime, there were physicists down in Princeton University, Peebles and Wilkinson, who had prophesized that radiation from the Big Bang would now be in a microwave region. And they were thinking about making an experiment to do it. In the meantime, Penzias and Wilson called them up and said, you know, we've been trying to get rid of this interference for years and we can't do it. What do you think it is? Well, at that time they realized they had actually found the CMB. So the people that didn't know what it was got a Nobel Prize for it. The people that had come up with the theory but hadn't built the experiment, you don't even know their names anymore. Peebles and Wilkinson. But when you see the full sky view of the cosmic microwave background, this picture was actually taken over a period of years. And the temperature is 2.725 Kelvin, which is just a little bit above absolute zero. So 2.725 Kelvin above absolute zero. So that's 2.725 degrees above that. But when you look at a weather map, you see blue and red and everything else, you think the temperatures are changing terribly. But here it's only 2/10,000ths of a degree between the hottest region and the coolest region of the CMB. So it's almost exactly uniform. But the inflationary theory was to find out, or to figure out why it wasn't uniform. And they figured out that with the inflationary theory, that may have caused the differences in temperature that you see there. So South Pole South Pole Telescope has gone through several different cameras that they've had on it. This is the latest one. It's called the 3G, and it has 16,140 detectors, which is about 2,690 pixels. It actually covers 1,500 square degrees of the sky, so that's about a 38 by 38 patch of the sky. And it runs, so if you look at the moon's about half a degree wide. So they're going 38 degrees wide. So you can think they're scanning a lot of the sky. They scan a lot of the sky at the same time, back and forth, back and forth, back and forth, all the time. And these detectors are aligned within 200 nanometers. If you think light goes about 5 feet in 1 nanosecond, a nanometer is very short. So basically with these detectors, they can detect very cold temperatures. They run it at a 1/4 of a degree above absolute zero. So they take liquid helium, which is at 4 degrees above absolute zero, run it through these pulse refrigerators down to about a 1/4 of a degree above absolute zero, and cool this whole array down to that temperature. And they do that because since you're detecting temperatures that are so low, any temperature above that would be interfering, kind of like if you're trying to take a picture and there's a bright flashlight in a way. The camera itself is actually pretty big, which you can see here, once that detector is mounted inside of it. The actual dish is above, aiming into that camera. There's a ground shield around that dish. The reason for the ground shield is because in the middle of winter, when they actually take the pictures with this telescope, it could get down to 100 degrees below zero Fahrenheit outside. But that's actually hot compared to the 2 degrees above absolute zero. So they don't want the heat of the 100 degree below zero snow reflecting up into the telescope. One of the more interesting things done with the South Pole Telescope is the Event Horizon Telescope. Basically, telescopes all over the Earth in different places you can see here are linked together to make basically a really large aperture. They don't gather any more light, in this case radio waves, but they do get a lot of resolution with it. And one of the first things they did was look at the M87 galaxy in the Virgo constellation. This is an extremely large galaxy. It's about 55 million light years away, and it's actually one of the most massive galaxies in the local universe, if you can consider 55 million light years the local universe. It's about 240,000 light years in diameter, which is slightly larger than the Milky Way, but it's much heavier. Its estimated mass is about 200 times that of the Milky Way. And it contains almost 1 trillion stars. What's interesting is that in the middle of this is a black hole, theorized to be a black hole, a gigantic black hole, really big. So if you look at the core of the galaxy here, they're looking at basically 1/100th of a degree, and that's where the core is. But in the middle of that, they've actually taken a picture of the shadow of the black hole. This is the first time that was ever done. The data was taken in 2017. The picture was released in April of 2019, last year. Basically, they did about 5 petabytes of data collected over a year, almost a year and a half. And that was flown to Max Planck Institute in Germany and to Haystack Observatory right here in Massachusetts. And a lot of supercomputer work was done to construct the image, which was released in April of 2019. The resolution of this picture is pretty phenomenal. It's 20 micro arc seconds. If you had a resolution of 20 micro arc seconds, you could read a newspaper in New York City from a cafe in Paris. So just think about how detailed that picture is. The other picture that I showed you, where it showed the core of the galaxy, was a 100th of a degree. This is 20 micro arc seconds in diameter. So what you see basically is the ring of gas that is around the black hole, and then the shadow of the black hole on it. They actually don't tie all these telescopes together. They synchronize them by atomic clock. They use hydrogen masers and to synchronize the time they're taking all the pictures, and then they combine all that once they fly all the data back to the observatories. They don't transmit it. They actually bring the hard drives back and load them onto their supercomputers. Why is it at the South Pole? Well, there's a lot of reasons. Once at high altitude, you have less atmosphere to look through. There's no sunrise and sunset, so that typically causes the atmosphere to be unstable. As you notice, usually in the evening here, when the sun goes down and you're at the beach, you get a little wind coming up. That you don't have happen there. It's very cold, so there's low water vapor. Microwave transmissions are really absorbed heavily by water vapor. And it's dark 24/7 in the middle of the winter, so you can have uninterrupted observations. And at the pole, you have another unique thing. You basically have the same patch of sky overhead. Although it's rotating, it's the same stars, the same clusters, the same galaxies overhead all year round. Second thing I'd like to talk about a little bit is the IceCube Neutrino Observatory. Basically, it's to study the high energy astrophysical processes, basically looking below the ice. It's actually pretty interesting. In Antarctica, the top maybe 150 foot of ice is melted snow, kind of compressed wet snow and glacier. But once you get down below that, it's optically pure. So the IceCube, the Neutrino Observatory, the neutrinos were first discovered in 1956. They're extremely small mass. They pass through normal matter unimpeded and undetected. So if you think about it, about 100 trillion neutrinos pass through your body every second, and you just don't know about it. Astronomy itself is kind of interesting. We started with visible wavelength, with optical telescopes, and then we went in both directions. We started looking at radio waves and gamma waves in the shorter wavelength, radio waves in the longer wavelengths. So then gravity waves were added. Now IceCube has added observations in neutrino decay to the tool chest of astronomy, and looking for the source of very high energy cosmic neutrinos. So a single cosmic ray proton from these high energy sources has enough energy to light a 50-watt bulb for 1 second. That's phenomenal for one proton. The processes that create the cosmic rays also create neutrinos. Now what's interesting is cosmic rays are electrically charged, so they're bent by the magnetic fields in space. They can go in all sorts of directions as they're bent. The neutrinos are not perturbed. They have no charge. So if you can see where the direction they came in through the Earth, you can point right back to their source and see exactly where they came from. The detectors are basically called DOMs, digital optical modules, and basically they're sunk down in the ice. There are 5,160 of these sensors drop down through the ice, and they start at about 0.9 miles below the surface, and they go down to 1.5 miles below the surface. They're dropped down on cables, and what they're looking for is the light coming up through the Earth, or the neutrinos coming up through the Earth and decaying, which they do very rarely along those lines. And these modules look for the radiation, the blue light radiation that comes off from the decay. Once you get below the ice, the top of the ice, as I mentioned, below the firn, you're in optically pure ice. So it's just like window glass. In fact, purer than window glass. So there's about a cubic kilometer of ice down there that these are detecting light going through. All this information from all those 5,160 modules are relayed up to the surface into what they call the counting house, and they are stored on optical discs and digital discs and hard disks, and they are also flown at the end of every winter. When summer comes around, they're flown back to the United States, and a new load of blank discs are shipped down because it's way too much to transfer over the satellite. What I found really interesting is how they actually drill these things, the hot water drilling. You can see the top picture there is the drilling mechanism that they use to drill down 1.5 miles. They use 4.7 million watts, 190 degree water, and 1,100 psi water pressure. And they used about 5,500 gallons of fuel per hole to power all these hot water drills. It takes about 30 hours to drill about 1.5 miles down. The size of these instruments are absolutely amazing for drilling. You can see in the lower right the hose reel, and it looks pretty big, but when you see it close up, you can see just how big that is. So all this equipment was flown down to the South Pole, taken on ship to McMurdo, and then put on C-130s and flown piece by piece to the South Pole. The first drill that goes down is the firn drill. That goes down for the first 150 feet, where I was mentioning the ice isn't purely clear. And that's basically a bunch of copper tubes running at a really high temperature. Once they get below that, they go through the enhanced hot water drill, and that goes all the way down to 1.5 miles. As they go down, they tape the cable onto the main cable, so the electrical cables onto the main cable that holds the whole thing from 1.5 miles down, and they use driller's tape. What's very interesting is our project, basically the total funding for our project is about the cost of the drilling tape they use on theirs. So how it works basically, as I mentioned, the high energy neutrinos come up through the Earth, they come through this array. Most of them, in fact, far majority of them never decay, so you never see them. But if they do decay, they cause a little flash of light. Each of these modules detect when that light happened, when the light hit them, and at what intensity. And with that, they can map the direction it came from and the intensity of the neutrino decay. And the idea here is to look back and see how far back, basically to see where this neutrino came from. Neutrinos also obviously come down from the solar system, from our sun. And an ice top, which is another array of these detectors on top of the ice, detect them and reject them. So they're only looking for the ones that come up through the Earth. And basically, yeah, the ice cube detector I mentioned is a cubic kilometer, and you could fit every person on Earth in a cubic kilometer if you actually measure it, which is pretty amazing. If a detector was the size of a person, it would take about 100 years for one neutrino to interact. And looking for the energies that IceCube is seeking, about 100,000 years. So that's why they need the really, really big 1 cubic kilometer detector. And so low energy neutrinos are produced all the time by the sun, supernova, relics from the Big Bang. But the high energy ones are produced by collisions of cosmic rays in our atmosphere, and extreme energy ones, the ones they're looking for, from black holes and neutron stars. IceCube is interested in the neutrinos that already had passed through the Earth, and every day about 275 atmospheric neutrinos are detected and rejected, about 100,000 a year. And in the first 3 years of operation, 28 neutrinos were generated outside of the solar system. So you think of this phenomenal big project, I think it cost $375 million to install. They detected 28 neutrinos in the first 3 years, but it was pretty phenomenal. Generated about a terabyte of data a day, and about 100 megabytes is sent home via satellite. The rest of it, as I mentioned, is sent home via hard drive. The most powerful neutrinos so far were actually named Bert, Ernie, and Big Bird. The origins were not certain. They didn't really know where they came from because they couldn't trace that line straight back. But they finally had found a long sought accelerator. And September 27, 2017, they found a blazar, which is basically a rotating quasar, which with the jets pointing towards the Earth. And it was confirmed with NASA's Fermi Gamma Ray Telescope and the MAGIC telescope. And so the blazar is basically a giant elliptical galaxy with a massive spinning black hole at its core, and twin jets of light emit elementary particles, and some of them happen to be pointed at the Earth, and that's what it detected. It's about 4 billion light years from Earth, and one of the most luminous sources known in the universe. Why at the South Pole? Again, why are these things at the South Pole? Well, for the IceCube Observatory, it's because the ice is optically clear, and you can't find a cubic kilometer of ice anywhere else that's optically clear. So you have a cubic kilometer of ice that acts as a detector, and it's ultra pure. Very, very, very clear. The next thing I'll talk about a little bit is space weather. Space weather, loosely defined, is kind of the interaction of the sun and the Earth and the space in between it and the upper layers of the atmosphere from things that happen on the sun. It's basically a study of physics of the sun-Earth environment. Many things that happen because of space weather that we don't typically think of. In the late 80s, basically the huge blackout in Quebec and parts of the northeast United States was caused by basically a storm on the sun. But it also has a lot of impacts on other things too. Astronaut safety, for example, if in the late, I guess it was also the late 80s, if the astronauts had been on the moon then, outside of their spacecraft, the radiation from that would have been enough to kill them. It also causes atmospheric drag, basically the particles coming from the mass ejections that would slow down satellites in orbit, so they actually have to use fuel to boost them up to a higher orbit. It also tends to cause errors in computer and memory upsets, solar cell damage, and charges the surface of spacecraft. It's very hard to get rid of charge that's on the surface of a spacecraft. Here, if you have a static electric charge, you can basically ground yourself by touching a piece of metal. Spacecraft don't have that. On the Earth, you have radio wave disturbances, so basically high frequency radio is disturbed, cellular disruption. Basically, you have GPS can be disturbed. More importantly, as I mentioned, the electric grid. The electric grid is disrupted tremendously because it induces really high currents on these long distance lines. It also can actually, believe it or not, wreck welds in long distance pipelines. The welds themselves, the welding material, is a little bit different than the metal that's in that makes up the pipe in the pipeline. So when these currents are induced on the pipeline, it will actually cause a galvanic disturbance where the welds are, and they can have leaks. So typically what they do now is when they detect these coming in, they put a bucking current in the pipeline going in the opposite direction to counteract that. Back when we used telecommunication cables with copper, now we mostly use fiber. That's actually what started most of the research on this, was that it caused terrible disruption on these long-distance lines that were going through the Atlantic Ocean between Europe and the United States. Here it gives you a little bit of idea how complex this environment really is. The sun pushes against the solar wind. The solar wind from the sun pushes against the magnetic fields of the Earth, basically causing a large magneto tail to go out to the right and pushing it in on the left. These magnetic fields come into the Earth through the north and south poles, magnetic poles, not the actual poles on the Earth, not where the Earth spins, but a little bit off a coast. And there's many different areas that can be studied here. So some of the instruments that are down in the South Pole are fluxgate magnetometers, which measure background magnetic fields and slow variations in the magnetic field. Induction coil, surge coil magnetometers, which measure very fast, about 100 cycles a second, magnetic field waves. Photometers and all-sky imagers, which record aurora and airglow emissions. There's different frequencies that are put out, and so you see different colors when you see the aurora. You see greens and blues and reds and things like that. Rheometers, which are imaging and broadband, and they look at particle precipitation and ionization in the upper layers of the atmosphere. GPS, similar to the one in your car, but typically with two frequencies, not one. And they map the total electron content that's in the ionosphere. And ELF and VLF receivers, which detect magnetospheric emissions, which you can hear as chorus, hiss, and whistlers. You can find them on the web if you look for whistlers. They're kind of interesting to hear. Why at the South Pole? Well, the magnetic field poles are near the South Pole. They're also near the North Pole, but the North Pole does not have any Earth. Underneath it is just floating ice, so you can't really set so many instruments there and leave them there for year after year. You got 24-hour continuous dark in the winter, so you basically can see the aurora. Look at the phenomena in the atmosphere. You have 24 hours of continuous light in a sun in the summer, so you can look at the sun, and there's no electromagnetic noise from motors starting up and things like that. New Jersey Institute of Technology also has some instruments at United Astronomy Clubs in New Jersey. We have a dual channel GPS to look at the ionosphere, a fluxgate magnetometer, which has been operating since 2008, takes one reading every second to look at the Earth's magnetic field, the direction and the intensity. A LIDAR, which is looking for gravity, basically, which are buoyancy waves in the upper atmosphere. And a reverse beacon network, which looks at ham radio signals that come in, and from that can detect basically how the ionosphere is moving up and down overhead by looking at how far away these signals are coming from. I'm not quite done yet. Talk a little bit about Antarctica itself, what it's like to travel down there. It's really an unusual place to be. I've gone there for 8 years now. It's got to be as close to being on another planet as you can be and not leave this one. It's very desolate once you get away from the hubbub of McMurdo and the hubbub of South Pole. There's really nothing out there. You're up on a plateau way high up above the Earth on ice. So most people, when they think of Antarctica, don't think it's very big. It kind of looks like a coffee stain at the bottom of a map. But it really is huge. It's about 1.5 times the size of the United States. And it's also got a lot of records going on with it. It's got the record low, which is 128 degrees below zero. Yearly average at the South Pole is 57 below zero. Almost the entire continent is covered with ice, and the ice averages 1.2 miles thick. In some places, it's 3 miles thick. Think about how thick that is. It's dry. There's about 8 inches of precipitation at the coast, but most of the continent is really considered a desert, inland desert. About 0.03% humidity at pole. Highest wind, sustained wind of 218 miles an hour. Vostok, which is the Russian station kind of in the middle of the plateau, the average wind speed there is 50 miles an hour. It's the highest continent of all, 6,500 foot in elevation. Much of it is above 9,800 foot in elevation. The highest mountain is a little over 16,000 feet. It's also very lonely. There's about 1,000 to 5,000 people scattered around the continent in the summer. Basically, at South Pole Station, the United States station, there's 140 in the summer, 40 in the winter. And when we go to the remote field sites where we do the space weather experiments, there's as few as 3 people, and we may be 300 to 500 miles away from the next person when you do that. How do you get there? Well, you fly typically from Newark to one of various places in the United States: Dallas, San Francisco, Los Angeles. But from there we go to Auckland, New Zealand, which is the North Island in New Zealand. Short hop to Christchurch, which is on the South Island. Then you go from there to McMurdo, which is another 2,300 miles. And then from McMurdo, you go on to the South Pole, which is basically, that's the wrong number there. It's about 830 more to the pole. First at Christchurch, you stop at the Clothing Distribution Center, where you get fitted with your emergency cold weather clothing. Now mind you, when I go down there, it's summer. It's kind of the warm time of year. The coldest it will typically get is about 40 below zero. In the winter, it will get very cold. The one thing though is in the summer you'll get more wind. In the winter you typically don't get the wind. But you get clothing that will take you through summer and winter. Those jackets are actually almost too hot to wear at times. The boots, typically the ones I have on there are Baffin boots. The soles are about 2 inches thick, so you do not get too cold. And you really get set up well so you can take care of yourself. In fact, a little bit too well, I think, at times. Sometimes you can fly down on the C-130, and when you do that, it can be packed. This is a picture from last year. We were so crowded in there, we basically had to interleave our legs to fit on the plane. Unbelievably crowded. But once you're flying, it's beautiful. You can get by one of the portals and look out. You can fly over the Transantarctic Mountains, which almost looks surreal. They're beautiful, and you can see all the glaciers flowing between the mountains, heading from the higher elevations down to the lower elevations. There's a couple different airports at McMurdo. McMurdo's on the shore. That's typically where all the distribution for everything for the South Pole for the United States is done. Willie Field is the one where wheeled planes can land. It's about 24 foot of compacted snow. That sits on about 8 to 10 foot of ice, and that's on top of about over 1,000 foot of water. And this one is the C-130 that we flew down on. Once you're at McMurdo itself, it's really not too pretty of a place, and it's actually in the midst of getting upgraded right now. It used to be a Navy depot, and at that point, a Navy base, and at that point, a lot of the buildings are still from that period and quite old. The whole island, because McMurdo is on Ross Island, which is actually just off the coast of Antarctica, the whole island is volcanic, so it's all kind of powdery, crushed volcanic rock everywhere you look underneath the snow. Once you get there, orientation and training is the same every year. There's a lot of it to go through. But one of the things you do find out is about how different the continent is. For example, the weather. Condition 3 is normal acceptable weather. Condition 2 starts when it gets between 75 to 100 degrees below zero, with wind and visibility that are low, high wind and low visibility. Condition 1 is when it's the worst. Condition 1 has winds greater than 55 knots, temperature colder than 100 degrees below zero, and visibility less than 100 feet. In Condition 1, you're not supposed to go outside. Typically what we have to do to get ready, though, is get all our camp gear and science gear together ready to go out to work on those field sites, deep field sites. And then we get on a LC-130 Hercules, which is like the C-130 Hercules that brought us in. But if you notice underneath it, there are actually skis under it instead of just wheels. At South Pole Station, nothing with wheels can land. And interestingly enough, these LC-130s are flowing out of New York State, the Air National Guard Wing, the 109th. Typically a lot less crowded going down there. You can see all the luggage in the middle. You sit on web seats and fly down. It's not a long trip to go to the South Pole from McMurdo. It's about 3.5 hours or so. Again, you're flying over the Transantarctic Mountains, a different area of them though, and they are just gorgeous. It's hard to get away from the windows, not just look at them, and just look at the beauty and just see how these rivers of ice, the very, very slowly moving rivers of ice going out from higher altitude to lower altitude, just basically pouring down. And you can see here where one is just starting in basically a pool of ice and snow and starting to move downhill on the lower left-hand corner there. And that's Beardsmore Glacier here, which is one of the biggest glaciers. It's tens of miles wide. Just a gigantic glacier, goes for actually hundreds of miles. South Pole Station is actually called NPX, which is very confusing. You'd think that would be North Pole Station, but South Pole Station is because it was originally Operation Deep Freeze was there from the Navy, so it's a Navy Pole Station, and that's where it got its NPX designation. When you land there, you're at 9,300 foot of elevation. 9,000 feet of that is ice. Only 300 foot is continent. I immediately get off the plane. The plane does not stop. The engines keep running. The propellers keep turning. Basically, they take the people off, the cargo off, and the plane immediately takes off and goes back. The reason they don't stop is just in case it didn't start again. It's quite an ordeal to get them going again because it's high altitude and it's cold, and they have to reheat all the engines, and they have basically all these huge pipes coming up from these called Herman Nelson heaters, and it takes a long time to get them going again. South Pole Station itself, there's been various stations over the years. The one that's currently there is actually kind of neat. It's almost like a five-star hotel. On the left-hand side there, where you see, let's see if I can get the cursor over there. This is where the galley is. This is typically the medical wing. This is where the science wing is. The dorms are here, here, and here, and this is basically a gymnasium here. So it's a pretty big area, and it's separated in half just in case there was a fire. You can get from one half to the other. This wing here also has an emergency generator in it that can take care of keeping that whole side of the station going should there be anything that catastrophic that happened like that. You can see it's lifted off the snow, and that's basically to keep it so the snow can run underneath it and the wind can go underneath it, so it does not get buried. The last station they had at the South Pole was a dome, a geodesic dome, and they had a lot of problems trying to keep the snow off of it, and basically gave up eventually and came up with this one. But it's actually pretty nice inside. Every winter, every January 1st, there's a moving the pole ceremony. There are two poles at South Pole. There's basically the ceremonial pole, which you've probably all seen, which is the series of flags, the 12 flags from the original signers of the South Pole Treaty, Antarctic Treaty. And then there's the actual South Pole. It moves year by year. It's not like the actual pole of the Earth is moving, but what this is you're on 9,000 feet of ice, and that 9,000 feet of ice is a glacier, and the South Pole Station and everything else around you moves all the time. It moves about 33 feet a year. So every January 1st, USGS comes out, surveys the site, finds out where the new South Pole is. You grab the site and move it. And then new actual South Pole marker is put there, which is accurate on January 1st, and by the end of December 31st, you're again off by 33 feet. Where we go to work on the deep field, we take small planes. They're called twin-engine otters. I kind of think of them as like the John Deere tractor of the sky. They're not fast. They go about 150 miles an hour. They're very powerful, though, and extremely reliable, and they land damn near anywhere. These are actually run by Ken Borick out of Canada. Every year they fly down from Canada, and every year they fly back to Canada. They get about 2.5 miles a gallon. When they're coming down and going back to Canada, they carry extra fuel on what are called ferry tanks, but still they have to stop time and time and time again all over. I think it's kind of a fun ride. But when we're inside, we basically have our cargo all strapped down. We sit in the back of the plane. They're unpressurized. It can get kind of cold in there, and depending on the time, you might be flying at quite a high altitude. We were up to 17,000 feet at times, and you can get a little bit short of breath up there. They're not the most comfortable planes in the world, but like I say, they're very, very sturdy. When you go over the Antarctic Plateau, though, it's just gorgeous. The beautiful desolation. Now you're away from the mountains, and there's nothing out there. It's just ice, deep, deep ice, miles deep ice as far as the eye can see in every direction. I mentioned 2.5 miles a gallon. You typically can't go 500 miles. In fact, you just can't unless you have one heck of a tailwind. So you have to stop and get fuel on the way. These fuel barrels are typically dropped but via parachute from a C-130 overhead, and then come up and straightened up here, and then they were pump them into the plane through that little 2-cycle engine that you see there through a filter, and away we go. We take the empties with us on the plane again. The place where we work, where we do the space weather experimentation, is called an AGO, an Automatic Geophysical Observatory. This is AGO 4. There are 5 of them on the continent. They're very small. They're 8 by 8 by 16 feet, and very hard to find unless you have the actual GPS coordinates, because there's nothing around. That picture that you saw before is kind of what it looks like. If you're 2 miles away from it, you're not going to see this thing. You have to be right on top of it. But we land there, get off the plane, get all our things out, get set up. First things first, and first things are typically melting some ice to make water for drinking, and get our instrumentation all uncovered, getting that ready to get worked on to get upgraded or repaired depending on what's necessary. Sometimes we work on automatic weather stations that we do for University of Wisconsin. This is Andy Stillinger up there working on one at AGO 4. We put them up. You can actually look on the internet and see what the current weather conditions are if you look for the automatic weather station from University of Wisconsin for AGO 4 and AGO 5, the 2 that we have up now. We also reorganized the caches. Basically, we have caches for food, fuel, and equipment, because it's possible to get stuck there. If the weather's bad, the plane cannot come back for you. And I think the longest, I have not had to do it, but Andy Stillinger and Bob Melville had to stay at one station. They were there for a week doing work. They were done with their work and had to stay there for an extra 16 days before the plane could come and get them. The food tends to keep really well because it's so darn cold there. It never gets anywhere near to, actually it never gets anywhere near to even 0 degrees. Andy Stillinger had some apple juice from 1995 and it was still perfectly good. Some of the pepperoni did start getting a little brown though. That's a picture of the AGO. You can see how they're powered in this picture. And there's the plane, the twin-engine Otter. After it dropped us off, it's on its way out. AGO has solar panels on the front and the back, 2 on each side, because remember, the sun's going overhead in the summer around your head. It does not rise or really set. It kind of just dips up and down a little bit if you're away from pole. And then you see the wind turbine off to the right. The blades on that are about 6 foot long each. That can generate 1,000 watts of power. That is actually the mainstay of our power generation, is the wind turbine. The solar panels obviously are only good in the summer to begin with, and they don't put out anywhere near that that power. I think they put out a total of about 200 watts. But just before we get ready to leave, taking a look around, it's just gorgeous. There's nothing out there, and it's just I just love the desolation. Well, we did get back to the South Pole. When we got back there, we had our 250th anniversary in Hope this year. So I took one of the t-shirts down and got a picture of the Hope t-shirt at the actual South Pole on January 1st. And then now we go back to McMurdo. This LC-130 has different props on it. You notice they're 8-bladed props instead of 4-bladed props. They're a little bit more fuel efficient. And supposedly vibrate a little less, but it's still noisy as heck in there and kind of shakes all the time. We got on one of these Deltas to ride out there. The Deltas are really, they're from the Navy. They're ancient vehicles from the 50s, late 50s, early 60s, but they just keep on going and going and going. Erebus Volcano. When we go to these AGOs, they're at a high elevation. Some of them are up over 11,000 foot elevation. So if you're going from sea level to 11,000 feet, you can have some real problems with altitude sickness. So being that you may not be able to get picked up right away, they really want you to be used to the altitude before you go there. So that's one of the reasons that we go to the South Pole and stay there for a while before we leave. We can do AGOs 1, 2, 3, and 4 from the South Pole because we'll stay at the South Pole for a week or two, get acclimated to the altitude, 9,300 foot, and then fly out to the AGOs. But AGO 5 has to be traversed from McMurdo. So we do that in 1 or 2 ways. One is to go to the Concordia station, which is the French-Italian station, which is up around 10,000 feet elevation. Wait there for a week or so, and then fly out. Or else go to the Erebus volcano. The Erebus volcano is the world's southernmost active volcano. It's actually one of only 3 in the world with a lava pool in it. And what we'll do is we fly out there on a helicopter, set up camp. You can see the 4 tents down there in the middle of nowhere. on Fang Ridge. That's called Fang Ridge. That was formed about 660,000 years ago. Last one of the really huge eruptions. That's what the ridges are there for. That was the edge of the caldera from the volcano. And we camp out there, and then fly down again by helicopter, right to the airfield. Get right on the airplane and go right to Ego 5. Ego 5 is the hardest one for us to get to. One of our troop basically climbed up to the very top of the volcano and took a look over the edge, to look at the sulfurous fumes. Apparently, it was very beautiful up there. I wish I could have done it, but I didn't. On the way home this year, we had an unnecessary part break on the airplane. And why I say that is basically we sat there for 5 hours waiting for the plane to come in. This was a C-17. C-17s are much bigger than the C-130s. Much faster. Instead of 8.5 hours from Christchurch to McMurdo, it only takes about 5 hours. Quieter, and especially bigger. That's the best part. But the pilot came in after 5 hours and said, a part broke on the airplane, but I think it's an unnecessary part. We should have it fixed in no time whatsoever and be off ground. Well, that didn't really happen. So we went back to McMurdo after 11 hours and got to see the first cargo ship come in. Got to see the fuel tanker come in. This is where all the fuel comes in. They keep 11 million gallons on site at McMurdo. And basically that's the fuel that also goes to fill up the 475,000 gallons at South Pole. And Coast Guard tied up next to that. The icebreaker basically comes in before all these three ships come in and creates a passage that goes out to the clear water. And then as it warms up and as the winds blow, the ice blows out and they end up with water like this that you can see. You'll see penguins here, you'll see Weddell seals. If you're lucky, you'll see excuse me, killer whales, and you'll also see some birds. You'll see snow petrels and skua. But eventually the unnecessary part was fixed. I think it was 5 or 6 days later, and we did get on the plane and flew. And you can see on a C-17, it really beats, even though it was completely full, it really beats a C-130. A lot of room on this plane. And if you ever wondered how the Southern Lights were really come on, there's the switch that turns them on. Anyhow, thank you for tuning in. I'm sorry it was so discombobulated. Sorry I've been so discombobulated. But I appreciate it. I'll be glad to entertain any questions you have and hopefully be a little bit better at doing that. Have a great day. No, I don't know how. Somebody was asking about Mount Erebus going all the way down, basically to the magma pockets down in the Earth. So when the Earth is shifting, when the crust still shifts, when we have the continental drift, doesn't that change? Yes, it does. Actually, that's why basically the whole island is there. Is basically from that volcano changing its position under the Earth's crust. And if you're there, you can also see a lot of small. There's actually quite a few volcanoes there that are extinct, and Erebus is the one that's active right now. But there's Mount Terror, which is one of the volcanoes too, a very big one. That used to be where Mount Erebus came out before it was Mount Erebus. But Ross Island itself is a volcanic island. The whole thing is volcanic, and that whole edge there is all basically from volcanoes moving under the Earth's crust, or actually the Earth's crust moving over the volcanoes, I should say.
Okay, so we're going to sign off now. If we see any more questions, we'll answer them on Facebook.
Sorry for the confusion.
If we can figure out how to stop this, we'll see.